Hey everybody. So I'm going to do another differential equation example. So we've looked at how to solve separable equations, right? And the idea with separable equations is when we have something of this form, right? We have a little method for solving them, but what I have here doesn't look like it's of that form, right? I don't have what's my f of y, what's my g of x. There's not two separate equations. However, with a small bit of algebra, I can factor out the x, and I get y squared minus 1. And so this gives me the two functions that I need, right? This x I can think of as g of x, and then f of y is going to be this y squared minus 1, right? So I just wanted to point out that if it doesn't necessarily look exactly like this, sometimes it can still be thought of that way, as long as you can write, right? In this case, g of x is x, f of y is y squared minus 1, and then it is exactly in that form. Okay, so let's keep going with this one. So we're just going to go ahead and follow our method. I take everything with y to the left-hand side, so I have 1 over y squared minus y dy, and all the x stuff I'll collect on the right-hand side. So now I've separated them, right? There's our separable equation. And then I want to integrate, right? I'm integrating the right side with respect to x and the left side with respect to y. So on the right-hand side, it's pretty straightforward. We get 1/2 x squared plus c, right? But the left-hand side might take a little bit of work, and there are several ways you might go about to do this. I'm going to do this work separately since it's going to take a bit of work. I notice one way to do this might be to notice that we can rewrite this as y minus 1, y plus 1, and this suggests that maybe partial fractions would work, right? It also has the form of one of the trig substitutions. I haven't tried that. It might work as well, but I'm going to go ahead with partial fractions here and see if I can solve this. So using the partial fraction decomposition, I can write, oops, move something out of the way for myself here. I can write that 1 over y minus 1, y plus 1 is equal to a over y minus 1 plus b over y plus 1, multiply through by the denominator. If you do the algebra over here, you'll get a plus b times y, and we'll have a minus b, right? So go ahead and I'll let you work out the details of that. You're just multiplying through by the denominator on the left-hand side and collecting like terms. And we know from this equation that the coefficient of y has to be 0, and the coefficient or the constant has to be 1, and I can simply add these two equations together. I get 2a equals 1, a is equal to 1/2, which is simple enough to see that b is equal to -1/2, okay? Which means I can rewrite this integral as the integral of 1/2 over y minus 1 plus -1/2 over y plus 1 dy. And these two integrals, these two antiderivatives, are easy enough to take. And we'll need a constant of integration, though I'm going to ignore it because I'm going to absorb everything into the constant. Remember, we're bringing all of this back in over here, over on the left side. However, I want to do one thing with these natural logs. So first of all, I'm going to factor out the 1/2. Oops, that's a minus. All right. Minus natural log y plus 1. I guess I shouldn't use the same. I'll just call it C1. I want to use one of the rules for natural logs, right? So because of the way natural logs are defined, there are some properties that can be derived from them. And one of them is that this, when you have a subtraction between two natural logs, you can turn it into a division within one natural log, right? So this is what the antiderivative ends up looking like, okay? So this is a nice, simple form. Especially, I'm just sort of thinking ahead that I'm going to have to solve for y. And so having it split across two natural logs doesn't seem like a great idea. So I'm going to take this and put it back in over here. And I'm going to ignore the constant and let this plus c over here absorb all the constants. So we'll have 1/2 the natural log of y minus 1 over y plus 1 is equal to this. Okay? All right, so now let's move forward. And we know from the definition, well, first let's get rid of the 1/2. So this is equivalent to y minus 1 over y plus 1 equals x squared. Again, I'm letting that 2 get absorbed into that constant of integration. There's no other constants floating around, so c just represents some number. Twice some number is still just some number, right? So because there's no conditions on c, it can be anything, so it doesn't need to absorb constants. We don't need to keep track of the constants in front of it. All right, so now we're going to use the definition of the natural log. The statement that I have here means that, oops, y minus 1 over y plus 1 is e to the x squared plus c. And I can rewrite this similar to how we did in the previous example. This becomes e to the c, e to the x squared. And then y minus 1 over y plus 1. This can become a constant. I'll just call it a1, e to the x squared. Okay? So far, so good. Now, I want to drop these absolute values. And so I can do that. Again, there's a plus or minus then implied, but because we have an arbitrary constant, it already could be positive or negative. So it's not really doing any good to have this here. And I don't really think I need the subscript. All right, so here we go with, we've got it broken down as much as we can very easily right now, right? But remember what I want to do. At the end of this problem, I want to have y by itself. And so right now I've got two y's floating around. They're on the same side. So this is a case where we kind of do something, I think of it as a knot or something like that. We've got to untangle something, we've got to go a little bit backwards to get back to where we started. So let's first multiply both sides by y plus 1. So I have a e to the x squared times y plus 1. Y minus 1 equals a e to the x squared times y plus a e to the x squared, right? Just distributing that. Now I'm going to bring everything with y to the left-hand side. Everything else goes to the right. So I'll have y minus a e to the x squared y equals 1 plus a e to the x squared. Okay, I can factor out a y. And then divide by this expression. Y equals 1 plus a e to the x squared over 1 minus a e to the x squared. Okay, so now this is our solution, right? And again, I'm going to leave it up to you. The way to check the answer is take the derivative. This would be a fairly, you know, it'll have some complications to it. We've got a quotient rule and we've got chain rules going on, but it's doable. And when you take the derivative, it should be the case that the derivative is equivalent to taking x times the square of that function and subtracting x from it, right? There's a lot of algebra in there. This is not necessarily the easiest one in the world to check, but nonetheless, there is our answer. Let's add one more piece to this, right? This is the general solution, right? So if we were to graph this, we could graph this, it would be a family of functions depending on the value of a, right? They would have slightly different qualities, and you can certainly program this into any graphing program you like. Some of them will handle a constant whose value you can shift, or you can just plug in manually different values and see what they look like, but you'll get some collection of functions. We pick out the one we care about by finding a particular value. So for instance, let's now find the value, let's find the particular solution such that y of 0 is equal to 1/3, right? So simply, all we do is write this. This implies, or another way to write this relationship, this means this graph goes through the point 0, 1/3, right? So, and what does it mean to go through that point? It means that the output value, the y value, is 1/3 when the input value is 0. So 1/3 is equal to 1 plus a over 1 minus a. We're going to do that same trick we just did a minute ago to get the a, to solve for a. I'm going to multiply it to the other side. I get 1/3 minus 1/3 a is equal to 1 plus a. I can add the 1/3 a to the other side and subtract 1. And I'll get, let's see, 1/3 minus 1 is equal to a plus 1/3 a. So now I have negative 2/3 is equal to 4/3 a, which means a is equal to negative 1/2. And there we have, oh, all right, I see my notes are wrong. This wasn't matching my notes, but I made a careless error in there. This looks good to me. All right, and so there we would have the particular solution in this case is that y is equal to 1 minus 1/2 e to the x squared over 1 plus 1/2 e to the x squared, okay? And that would be the particular solution in this case, right? Picking out that one function among all of them that satisfies these initial conditions. All right, so that was a pretty long one, but every step along the way is you know, easily doable, right? We start with our separable equation. We have to do a little bit of factoring, and then we just take some integrals. One of them turned out to be an integral with some work. I highly recommend. There's no reason to do all this work in my little space over here, so I did a little bit of work off to the side. Once we have the antiderivative, it was just an algebra problem from that point forward, solving for y, and then solving for the constant with the given information. Okay, that's it for this one. Thanks, everybody. See you next time.